Okay. So what we have here. So first of all, this is the interactive cave, three-dimensional cave part of our VOCC facility in Castle and in Oak Ridge. Basically, what we use this facility for is to look at big three-dimensional models of the simulations we're running inside of Castle, and obviously those are particularly pertaining to nuclear power reactors. So,
and real quick, what's Castle?
Okay, so where have they been through? Okay, this is a Titan thing, right? So Castle's our DOE Nuclear Energy Innovation Hub for it's the acronym is the it's a really terrible acronym.
That's fine. Yeah,
Consortium of Advanced Simulations of Light Water Reactors. Yes. It's a terrible acronym.
That's a good acronym.
See, whenever I think of Castle, I think of Capillary Soccer League from Raleigh. So anyway, anyhow, so yeah, I was at a talk once where some guy was talking about astrophysics stuff, and somebody asked me, "Well, how big is that thing?" He's like, "I don't know." And it's the same thing. Well, what does Castle mean? I don't know. I just always say. Anyhow, so anyway, this is a three-dimensional cave, and what we do is this is fairly configurable. So obviously we've got panels top, bottom on either side, and these actually roll out to the side, so you can do all sorts of different things when you're looking at a big three-dimensional model. And so what I've got in here is this is the calculation that we ran on Titan of a full core PWR, and what I did is I cut it off, so we're only looking at a quarter of it, so we can look down the core.
So real quick, 4-core PWR?
I'm going to get to that.
Okay.
Okay. So in other words, this is a pressurized water reactor,
okay.
Which is it's a standard model. This is the most common type of reactor we have in the nuclear industry operating in the United States today. There are other types of designs, but the vast majority are PWRs. Basically, what they do is they actually have a steam exchange, hence the pressurized. To keep the water from boiling, you have to run it at pressure. Right?
Okay.
All right. So the water goes through, and then it hits steam exchangers. It goes through the core, and if you didn't have it at high pressure, it would boil off.
Okay.
All right? So that's why they're called pressurized water reactors. What we're looking at here, obviously, is what drives the power in a nuclear reactor. Is really very much a function of the distribution of neutrons, and in a PWR in particular, it's the distribution of low energy, or what we call thermal neutrons. Right. So what we're looking at here is a big three-dimensional calculation of the thermal neutron distribution, and that's that lower part by color. So the neutron distribution is high in the reddish zones, and it's low in the blue-green zones. Right. And then on top, we're looking at the power rod. So basically the way these nuclear reactors are configured is they're basically, the reactor is designed in lattices, and generally in most PWRs they're 15 by 15 or 17 by 17 arrays of small cylindrical fuel pins. And these fuel pins are not big. They're on the order of half an inch, okay, in radius,
okay,
diameter, I should say. But they're tall. So they're 12 to 15 feet tall. So each of these, so you have these lattices, and then you actually build the core in arrays of lattices. So you have arrays of fuel pins assembled into arrays of lattices. Okay, and so and then they load the fuel with different, in what we call enrichments of the uranium or the fissionable isotopes to control the population of neutrons over the life cycle of the fuel. And ultimately, what dictates the efficiency of how these cores run is how often you have to switch the fuel. All right, so when they first started licensing these reactors, back in the 50s, 60s, not necessarily this design, but designs like it, they were very conservative about when they needed to do fuel switching. And the thing is, when you switch the fuel, you don't fully burn the fuel, so actually you leave power in the fuel, as it were. It'd be like, taking the gasoline out of your car and switching it when you still had a quarter tank left.
Yeah.
Right? So you're leaving power, you're putting power in the trash, as it were. And also, when you bring the reactor down, it's an expensive process. You have to bring the reactor down, you have to bring the health physics in, you have to do the radiation protection exercises, you got to move the fuel out, move the fuel in, and all that time you're not generating electricity. So the longer that period can be spread out, the more efficient more reactors run, the more power you get out. Ultimately, the more electricity you produce per dollar.
Okay.
All right. So a lot of what Castle is attempting to do is to use big 3D simulations or better simulations involving computers like here at the Oak Ridge Leadership Computing Facility to do better, more detailed models to improve the uprates of these reactors. Okay, in other words, allow them to operate longer with confidence, so that they don't have to shuffle fuel quite as often. There's other problems that exactly we're looking at too, that we call challenge problems that the industry is dealing with, that their current set of computational tools aren't capturing. All right. So that's not the only thing. So there's several features what we're trying to do, all to improve the efficiency of how well they can operate the reactors, and ultimately correlates into dollars per megawatt.
So what does this box let you do?
So what this box lets us do is these 3D calculations are very complex. So for example, the data you're looking at here really is really on the order of terabytes of data. All right, distilled down to an image that we can actually see. Your mind can't process. I can't show you a spreadsheet with a terabyte of numbers on it, and you can't make nobody can make sense of it. So we have to put these things in a way that we can look at it. And one of the values of this is you take the facility like this combined with our kind of high performance 3D visualization software. This is done with a tool called Visit that's both developed at Oak Ridge, Livermore, and across the DOE complex, that's very efficient for taking terabytes of actually numerical data and putting it into a three-dimensional image that we can look at. And what the value of this facility is, a analyst can come in after running a calculation and look at certain features that they want to see. First of all, they can get the bird's eye view and say, okay, this was a hot zero power, which means it was fresh fuel. So this calculation should show certain things. So for example, it should be symmetric, right? The fuel should be burning symmetrically. And that's what we see. So, I mean, that seems like, oh, well, that's obvious, right? But the reality is when you have that much data, you can't just look at a few integrated points and determine, is it really correct?
Yeah. Okay,
so from a big picture, I can look at this thing and say, okay, things are actually burning symmetrically, that's good. Am I seeing the power peaking where I expect it to? Yes, okay, so the first thing you do is there's a whole series of heuristic type things I can do to say, all right, I'm beginning to believe this calculation is some manifestation of truth. All right, now once I've kind of determined that, I can actually go and start to look at certain features that I might want to look at. So for example, AJ, could you lift this up just a little bit?
So how is he? What's going on?
So he's using this interactive joystick. There's two ways to interact with the cave. One is with this interactive joystick. The other one, which I'll show you in a minute, is with these goggles. But anyway, so the other thing we can do is say, okay, so now we can start spinning this around and we can start looking at axial features down the core, and we can look at we can look at the radial, axial, and before, the way people used to look at these things, they would make a two-dimensional slice and put it up there, and then take a step down and look at another two-dimensional slice, take a step down. Well, you can miss stuff when when you're not looking at the whole assembly of the data. And so this allows you to kind of get that full 3D view of the data. And then, AJ, give me the goggles here. Thank you. So then the next thing you can do is you can use these geek goggles I have here. And when you actually put these on, then the image actually follows your movements. And actually, you can actually start now really walking interactively through the core and looking at various things. So I can look up at different power rods, I can look down axially at the thing, I can back up. All right, and it almost gets you the sense that you're actually, reaching out and touching it. Now I'm doing this because this actually also works in three dimensions. These are 3D goggles, which is why when you're just looking at the thing without these, it looks a little bit stereotopic.
Yeah, I
right?
gotcha.
So
now, is this all the computations were done ahead of time?
Yep.
Right, and you're manipulating that data in real time.
That's right.
Okay.
So the calculation here is something that this particular calculation is something that can only be done on a machine like Titan.
And how long would it take, just an average, to
So
run
on
this
this series of calculations, we actually did several different permutations of this core. The largest model we did had 10 to the 15th total unknowns in it, and it ran, I think, on the order of 40 to 45 minutes on 275,000 cores, which is nearly the whole machine.
Okay.
The whole Titan machine before this latest upgrade.
Okay.
So we haven't actually started running it on the new configuration yet, because that's only just, as you guys know, happening today.
Yeah, I gotcha. Cool.
Right. But the thing is, so the only way you could run this type of calculation is on a machine with that kind of horsepower behind it. This isn't something that you could do on a desktop. And once you then have the output, then we go and we have the OLCF has what we call visualization clusters. All right, and those are 512, 1024 type node clusters, which are big by conventional standards, but not big by Titan standards. And they're dedicated solely to doing data processing and analysis. So it takes this terabytes of output that we produced on Titan, and we set up on the back end a compute server that processes that data and then just simply sends the graphics commands over to our local desktop here, and that desktop then controls this. So,
Okay.
so we can sit down, I can sit down, and I've done this before. You know, I've sat down at a hotel room in a conference and brought my laptop up, connected to our visualization cluster, and brought images like this up on my laptop, because we're doing all the heavy lifting on site here
Yeah.
on the back end cluster, and only bringing the front end graphics commands to the desktop.
Cool.